This is the second part of the second colligative properties video. The recording stopped on me, so just picking up here at the second page of that second colligative properties video. In the middle of the problem here, just writing the equation, we know that the change in temperature of the freezing point of the solution will be equal to the molality of the solution times the freezing point depression constant. So as always, we need to calculate the molality. In situations here where we don't have water, make sure you're paying attention to what the solute is and what the solvent is. We're dissolving ethanol in chloroform, so ethanol would be the solute. So I want to know how many moles of ethanol do I have dissolved per kilogram of the chloroform. That's what I'm looking for. Okay, so I have 16.7 grams of the ethanol, and I'm dissolving it in 150 grams, so that'd be 0.150 kilograms of the chloroform. Alright, so from here we just have a gram to mole conversion for the ethanol. The molar mass of ethanol is 46.068 grams of ethanol per mole of ethanol. Grams cancel. And we're left with moles of ethanol per kilogram of chloroform. Now note that ethanol is not electrolytic, so it's not going to break apart into more particles, so it's just the gram to mole conversion. And this should give you 2.42 molal. From here we can just use our freezing point depression equation. Just slide that down here. Our molality is 2.42 molal times the depression constant for chloroform of negative 4.68 degrees Celsius per molal. The reason why it's negative is because the freezing points go down. So all freezing point depression constants are negative. The boiling point elevation constants are positive. Again, notice your units, molal units cancel. We're left with degrees Celsius. This gives us a change in freezing point of negative 11.3 degrees Celsius. Again, this is not our answer. This is how much the freezing point changed by. To find the freezing point of the solution, we need to factor in the normal freezing point, which for chloroform is the negative 63.5 degrees Celsius. It's going to go down by 11.3 degrees Celsius. So this gives us a value of negative 74.8 degrees Celsius is the freezing point of the solution. And there's our answer there. All right, the last example here is dealing with that last learning target about finding the molar mass. We're told that the organic compound aluminon is used as a reagent to test for the presence of the aluminum ion in aqueous solution, and then a solution of 2.5 grams of aluminon in 50 grams of water freezes at negative 0.197 degrees Celsius. What is the molar mass of the aluminon? And we're given the freezing point depression constant of water, and we were also told that the aluminon is non-electrolytic. So here we are already given the freezing point depression of the solution. We know this is the freezing point, considering that water freezes at at 0 degrees Celsius. That's also how much the freezing point went down by. So just looking at our freezing point depression equation, just copying that down here. The only thing I don't know is the molality, so that's what I'm going to find. I'm going to solve the equation for that. The molality would be the change in the freezing point divided by the freezing point depression constant. Plugging in our values, this is how much the freezing point went down by. So negative 0.197 degrees Celsius divided by the freezing point depression constant of negative 1.8 degrees Celsius per molal. Notice you're left with molal units now. This should give you 0.106 molal. Alright, considering our units here, remember that is moles of solute per kilogram of solvent. So I know that I have 50 grams of water, that's 0.050 kilograms of water. I can use my molality as a conversion factor. I know that every kilogram of water will contain 0.106 moles of the aluminon. And this would tell me how many moles we have. I get 0.05 0.00530 moles of the aluminum. That's what I get there. I'm sorry, my handwriting is a little sloppy there. Alright, so you might be thinking, how do I get molar mass? Well, I know how many moles were there. We're also told the mass. There's 2.5 grams of the aluminum in there. I know the units on the molar mass are grams per mole, so it's just a simple division. 2.50 grams of the aluminum represents 0.00530 moles, and that would give us the molar mass, which is 472 grams per mole. And there we are. All done there. Alright, going on to the practice problems here. I'd stop the video, try these yourselves, and check out how exactly you did. Alright, first question on the practice problems is a little different than the examples. We're asked to find the mass of potassium permanganate that must be added to 1.75 kilograms of water to lower the freezing point of the solution by 0.5 degrees Celsius. Again, here's an example where we're given the depression, so we should just be able to find the molality and then use that in order to find the mass. That would be our strategy here. So just using the same equation we just actually used above, the molality would equal the change in freezing point divided by the freezing point depression constant. So the change in freezing point, again, because the freezing point of water is 0, this freezing point, the negative 0.5, is also the change in the freezing point. So negative 0.500 degrees Celsius divided by the freezing point depression constant of water, which we already used before. That's the negative 1.86 degrees Celsius per molal. This should give you a value, I'm doing it for the first time here, is 0.269 molal. So we get there. Alright, so again, remember like we did before, we can use that as a conversion factor. We have 1.75 kilograms of water, and I know that every kilogram of water will contain 0.269 moles of particles. Now, if potassium permanganate were a non-electrolyte, this would be all I would need to do. Well, I need to do a mole to gram conversion. But the fact that potassium permanganate is an electrolyte, if you're not sure of the formula, it is KMnO4. So this will break into two ions, a potassium ion and a permanganate ion. So for every 2 moles of particles, I get 1 mole of the KMnO4. From there, I can now use a molar mass to find the mass of the potassium permanganate. Let's see, I need to calculate that molar mass here. Let's see, potassium 39.1 plus the manganese of 54.94 plus 4 moles of oxygen. I get 158.04 grams KMnO4 per mole. KMnO4. And that should give us the answer. Let's go ahead and plug it in here. So 1.75 times 0.269 divided by 2 times 158.04. Let's see, looks like 3 sig figs. I get 37.2 grams KMnO4. And we're done. Oh, yeah, that's right, 37.2. Alright, next practice problem. We're told the boiling point of a solution made by dissolving 31.5 grams of, I don't think this question is written correctly. Oh, we're supposed to find the boiling point. Yeah, that's what we're asked to do. Okay, so I'm going to change this. What is the boiling point? What is the boiling point? This will make much more sense. What is the boiling point of a solution made by dissolving this mass of methanol in 258 grams of acetic acid? And it gives us the data here on the normal boiling point of acetic acid and its boiling point elevation constant. Alright, so we need to find how much the boiling point is going to go up by. So the change in temperature of the boiling point times molality times the boiling point elevation constant is what we need to find. So we need to find the molality. Remember, solute over solvent, methanol is our solute. So I have 31.5 grams of the methanol CH3OH for every 258 grams of the acetic acid. Alright, so molality is moles per kilogram. So I need a mole to gram to mole conversion. So molar mass of methanol is 32.05 grams C2H5OH per mole. Actually, not C2H5. I was thinking ethanol. That's CH3OH. I did calculate the right molar mass, though. And then I could have just put that in kilograms to start with. I'll go ahead and do that conversion here. There are 1,000 grams per kilogram. Okay, and this will give us the molality. So 31.5 divided by 258 divided by 32.05 times 1,000. That gives me a molality of 3.81 molal. I can use that in our equation here. I'm not showing you guys what's going on here. We can use that in our equation here for the boiling point elevation. So I have 3.81 molal. 3.81 molal times the boiling point elevation constant of 2.93 degrees Celsius per molal. This gives you, get it plugged in here, looks like 3 sig figs, 11.2 degrees Celsius. Remember, this is not the answer. This is what the boiling point changed by. It's going to go up. Here's its boiling point elevation. So I have my 118 degrees Celsius for the normal boiling point plus the 11.2 degrees Celsius. As far as sig figs are concerned here, remember the addition you should really only keep to the ones place here because that's all the farther that first measurement goes. Your calculator is going to tell you, what would that be, 129.2. I would just round that to 129 degrees Celsius. And there we are.